probability distribution.
In probability and statistics, a probability distribution assigns a probability to each measurable subset of the possible outcomes of a random experiment, survey, or procedure of statistical inference. Examples are found in experiments whose sample space is non-numerical, where the distribution would be a categorical distribution. Experiments whose sample space is encoded by discrete random variables, where the distribution can be specified by a probability mass function. And experiments with sample spaces encoded by continuous random variables, where the distribution can be specified by a probability density function. More complex experiments, such as those involving stochastic processes defined in continuous time, may demand the use of more general probability measures. In applied probability, a probability distribution can be specified in a number of different ways, often chosen for mathematical convenience. By supplying a valid probability mass function or probability density function, by supplying a valid cumulative distribution function or survival function, by supplying a valid hazard function, by supplying a valid characteristic function, by supplying a rule for constructing a new random variable from other random variables whose joint probability distribution is known. A probability distribution can either be univariate or multivariate. A univariate distribution gives the probabilities of a single random variable taking on various alternative values. A multivariate distribution, a joint probability distribution, gives the probabilities of a random vector, a set of two or more random variables, taking on various combinations of values. Important and commonly encountered univariate probability distributions include the binomial distribution, the hypergeometric distribution, and the normal distribution. The multivariate normal distribution is a commonly encountered multivariate distribution.
Introduction.
To define probability distributions for the simplest cases, one needs to distinguish between discrete and continuous random variables. In the discrete case, one can easily assign a probability to each possible value. For example, when throwing a fair die, each of the 6 values 1 to 6 has the probability 1/6. In contrast, when a random variable takes values from a continuum, probabilities can be non-zero only if they refer to intervals. In quality control, one might demand that the probability of a 500G package containing between 490G and 510G should be no less than 98%. If the random variable is real-valued, or more generally, if a total order is defined for its possible values, the cumulative distribution function, CDF, gives the probability that the random variable is no larger than a given value. In the real-valued case, the CDF is the integral of the probability density function, PDF, provided that this function exists.
Terminology.
As probability theory is used in quite diverse applications, terminology is not uniform and sometimes confusing. The following terms are used for non-cumulative probability distribution functions. Probability mass function, PMF for discrete random variables, categorical distribution, for discrete random variables with a finite set of values, probability density function, PDF, most often reserved for continuous random variables. The following terms are somewhat ambiguous as they can refer to non-cumulative or cumulative distributions, depending on authors' preferences. Probability distribution function, continuous or discrete, non-cumulative or cumulative. Probability function, even more ambiguous, can mean any of the above or other things. Finally, probability distribution, sometimes the same as probability distribution function, but usually refers to the more complete assignment of probabilities to all measurable subsets of outcomes, not just to specific outcomes or ranges of outcomes.
Basic terms.
Mode, for a discrete random variable, the value with highest probability, the location at which the probability mass function has its peak. For a continuous random variable, the location at which the probability density function has its peak. Support, the smallest closed set whose complement is probability 0. Head, the range of values where the PMF or PDF is relatively high. Tail, the complement of the head within the support. The large set of values where the PMF or PDF is relatively low, expected value or mean, the weighted average of the possible values, using their probabilities as their weights. Or the continuous analog thereof, median, the value such that the set of values less than the median has a probability of 1/2, variance, the second moment of the PMF or PDF about the mean. An important measure of the dispersion of the distribution, standard deviation, the square root of the variance, and hence another measure of dispersion, symmetry, a property of some distributions in which the portion of the distribution to the left of a specific value is a mirror image of the portion to its right, skewness, a measure of the extent to which a PMF or PDF leans to one side of its mean.
Cumulative distribution function.
Because a probability distribution PR on the real line is determined by the probability of a scalar random variable x being in a half-open interval x, the probability distribution is completely characterized by its cumulative distribution function.
Discrete probability distribution.
A discrete probability distribution shall be understood as a probability distribution characterized by a probability mass function. Thus, the distribution of a random variable x is discrete, and x is then called a discrete random variable, if as u runs through the set of all possible values of x. It follows that such a random variable can assume only a finite or countably infinite number of values. For the number of potential values to be countably infinite even though their probabilities sum to 1 requires that the probabilities decline to 0 fast enough, for example, if for n equals 1, 2. We have the sum of probabilities 1/2 plus 1/4 plus 1/8 plus equals 1. Among the most well-known discrete probability distributions that are used for statistical modeling are the Poisson distribution, the Bernoulli distribution, the binomial distribution, the geometric distribution, and the negative binomial distribution. In addition, the discrete uniform distribution is commonly used in computer programs that make equal probability random selections between a number of choices.
Cumulative density.
Equivalently to the above, a discrete random variable can be defined as a random variable whose cumulative distribution function, CDF, increases only by jump discontinuities, that is, its CDF increases only where it jumps to a higher value, and is constant between those jumps. The points where jumps occur are precisely the values which the random variable may take.
Delta function representation.
Consequently, a discrete probability distribution is often represented as a generalized probability density function involving Dirac delta functions, which substantially unifies the treatment of continuous and discrete distributions. This is especially useful when dealing with probability distributions involving both a continuous and a discrete part.
Indicator function representation.
For a discrete random variable x, let u0, u1 be the values it can take with non-zero probability. Denote. These are disjoint sets, and by formula, 1. It follows that the probability that x takes any value except for u0, u1 is 0, and thus one can write x as except on a set of probability 0, where is the indicator function of a. This may serve as an alternative definition of discrete random variables.
Continuous probability distribution.
A continuous probability distribution is a probability distribution that has a probability density function. Mathematicians also call such a distribution absolutely continuous, since its cumulative distribution function is absolutely continuous with respect to the Lebesgue measure L. If the distribution of x is continuous, then x is called a continuous random variable. There are many examples of continuous probability distributions, normal, uniform, chi-squared, and others. Intuitively, a continuous random variable is the one which can take a continuous range of values, as opposed to a discrete distribution, where the set of possible values for the random variable is at most countable. While for a discrete distribution an event with probability 0 is impossible, For example, rolling 31/2 on a standard die is impossible, and has probability 0. This is not so in the case of a continuous random variable. For example, if one measures the width of an oak leaf, the result of 31/2 centimeters is possible, however it has probability 0 because there are uncountably many other potential values even between 3 centimeters and 4 centimeters. Each of these individual outcomes has probability 0, yet the probability that the outcome will fall into the interval, 3 centimeters, 4 centimeters, is non-zero. This apparent paradox is resolved by the fact that the probability that x attains some value within an infinite set, such as an interval, cannot be found by naively adding the probabilities for individual values. Formally, each value has an infinitesimally small probability, which statistically is equivalent to 0. Formally, if x is a continuous random variable, then it has a probability density function f, x, and therefore its probability of falling into a given interval, say, is given by the integral. In particular, the probability for x to take any single value a, that is a, x, a, is 0, because an integral with coinciding upper and lower limits is always equal to 0. The definition states that a continuous probability distribution must possess a density, or equivalently, its cumulative distribution function be absolutely continuous. This requirement is stronger than simple continuity of the cumulative distribution function, and there is a special class of distributions, singular distributions, which are neither continuous nor discrete nor a mixture of those. An example is given by the Cantor distribution. Such singular distributions, however, are never encountered in practice. Note on terminology: some authors use the term continuous distribution to denote the distribution with continuous cumulative distribution function. Thus, their definition includes both the absolutely continuous and singular distributions. By one convention, a probability distribution is called continuous if its cumulative distribution function is continuous and, therefore, the probability measure of singletons for all. Another convention reserves the term continuous probability distribution for absolutely continuous distributions. These distributions can be characterized by a probability density function, a non-negative Lebesgue integrable function defined on the real numbers such that discrete distributions and some continuous distributions, like the Cantor distribution, do not admit such a density.
Some properties.
The probability distribution of the sum of two independent random variables is the convolution of each of their distributions. Probability distributions are not a vector space, they are not closed under linear combinations, as these do not preserve non-negativity or total integral 1, but they are closed under convex combination, thus forming a convex subset of the space of functions, or measures.
Kolmogorov definition.
In the measure-theoretic formalization of probability theory, a random variable is defined as a measurable function x from a probability space to measurable space. A probability distribution is the push-forward measure, p, satisfying xp equals px. 1 on.
Random number generation.
A frequent problem in statistical simulations, the Monte Carlo method, is the generation of pseudo-random numbers that are distributed in a given way. Most algorithms are based on a pseudo-random number generator that produces numbers x that are uniformly distributed in the interval 0, 1. These random variates x are then transformed via some algorithm to create a new random variate having the required probability distribution.
Applications.
The concept of the probability distribution and the random variables which they describe underlies the mathematical discipline of probability theory, and the science of statistics. There is spread or variability in almost any value that can be measured in a population, for example height of people, durability of a metal, sales growth, traffic flow, etc. Almost all measurements are made with some intrinsic error. In physics, many processes are described probabilistically, from the kinetic properties of gases to the quantum mechanical description of fundamental particles. For these and many other reasons, simple numbers are often inadequate for describing a quantity, while probability distributions are often more appropriate. As a more specific example of an application, the cache language models and other statistical language models used in natural language processing to assign probabilities to the occurrence of particular words and word sequences do so by means of probability distributions.
Common probability distributions.
The following is a list of some of the most common probability distributions, grouped by the type of process that they are related to. For a more complete list, see List of probability distributions, which groups by the nature of the outcome being considered, discrete, continuous, multivariate, etc. Note also that all of the univariate distributions below are singly peaked. That is, it is assumed that the values cluster around a single point. In practice, actually observed quantities may cluster around multiple values. Such quantities can be modeled using a mixture distribution.
Related to real-valued quantities that grow linearly, for example errors, offsets.
Normal distribution, Gaussian distribution, for a single such quantity. The most common continuous distribution.
Related to positive real-valued quantities that grow exponentially, for example prices, incomes, populations.
Log normal distribution, for a single such quantity whose log is normally distributed. Pareto distribution, for a single such quantity whose log is exponentially distributed. The prototypical power law distribution.
Related to real-valued quantities that are assumed to be uniformly distributed over a possibly unknown region.
Discrete uniform distribution, for a finite set of values, for example the outcome of a fed eye. Continuous uniform distribution, for continuously distributed values.
Related to Bernoulli trials yes-no events, with a given probability.
Basic distributions. Bernoulli distribution, for the outcome of a single Bernoulli trial, for example success-failure, yes-no. Binomial distribution, for the number of positive occurrences, for example successes, yes votes, etc. given a fixed total number of independent occurrences. Negative binomial distribution, for binomial type observations but where the quantity of interest is the number of failures before a given number of successes occurs. Geometric distribution, for binomial type observations but where the quantity of interest is the number of failures before the first success. A special case of the negative binomial distribution, Bernoulli distribution, for the outcome of a single Bernoulli trial, for example success-failure, yes-no. Binomial distribution, for the number of positive occurrences, for example successes, yes votes, etc. given a fixed total number of independent occurrences. Negative binomial distribution, for binomial type observations but where the quantity of interest is the number of failures before a given number of successes occurs. Geometric distribution, for binomial type observations but where the quantity of interest is the number of failures before the first success. A special case of the negative binomial distribution, related to sampling schemes over a finite population. Hypergeometric distribution, for the number of positive occurrences, for example successes, yes votes, etc. given a fixed number of total occurrences, using sampling without replacement. Beta binomial distribution, for the number of positive occurrences, for example successes, yes votes, etc. given a fixed number of total occurrences. Sampling using a Polyerns scheme, in some sense, the opposite of sampling without replacement. Hypergeometric distribution, for the number of positive occurrences, for example successes, yes votes, etc. given a fixed number of total occurrences, using sampling without replacement. Beta binomial distribution, for the number of positive occurrences, for example successes, yes votes, etc. given a fixed number of total occurrences. Sampling using a Polyerns scheme, in some sense, the opposite of sampling without replacement.
Related to categorical outcomes events with k possible outcomes, with a given probability for each outcome.
Categorical distribution, for a single categorical outcome, for example yes-no may be in a survey. A generalization of the Bernoulli distribution, multinomial distribution, for the number of each type of categorical outcome, given a fixed number of total outcomes. A generalization of the binomial distribution, multivariate hypergeometric distribution, similar to the multinomial distribution, but using sampling without replacement. A generalization of the hypergeometric distribution.
Related to events in a Poisson process, events that occur independently with a given rate.
Poisson distribution, for the number of occurrences of a Poisson-type event in a given period of time. Exponential distribution, for the time before the next Poisson-type event occurs. Gamma distribution, for the time before the next k Poisson-type events occur.
Related to the absolute values of vectors with normally distributed components.
Rayleigh distribution, for the distribution of vector magnitudes with Gaussian distributed orthogonal components. Rayleigh distributions are found in RF signals with Gaussian real and imaginary components. Rice distribution, a generalization of the Rayleigh distributions for where there is a stationary background signal component. Found in Rishon fading of radio signals due to multipath propagation and in MR images with noise corruption on non-zero NMR signals.
Related to normally distributed quantities operated with sum of squares for hypothesis testing.
Chi-squared distribution, the distribution of a sum of squared standard normal variables. Useful for example for inference regarding the sample variance of normally distributed samples, see chi-squared test. Student's t-distribution, the distribution of the ratio of a standard normal variable and the square root of a scaled chi-squared variable. Useful for inference regarding the mean of normally distributed samples with unknown variance, see student's t-test. F-distribution, the distribution of the ratio of two scaled chi-squared variables. Useful for example for inferences that involve comparing variances or involving the squared correlation coefficient.
Useful as conjugate prior distributions in Bayesian inference.
Beta distribution, for a single probability, real number between 0 and 1. Conjugate to the Bernoulli distribution and binomial distribution. Gamma distribution, for a non-negative scaling parameter. Conjugate to the rate parameter of a Poisson distribution or exponential distribution, the precision, inverse variance, of a normal distribution, etc. Dirichlet distribution, for a vector of probabilities that must sum to 1. Conjugate to the categorical distribution and multinomial distribution. Generalization of the beta distribution, a sharp distribution, for a symmetric non-negative definite matrix. Conjugate to the inverse of the covariance matrix of a multivariate normal distribution. Generalization of the gamma distribution.